We're looking at proving your Mayer's relation, which talks about Cp minus Cv is equal to R. So this is our agenda to prove this. So your proof starts with listing out all the things that we know. Starting off with PV is equal to nRT. Since we are looking at molar specific heat, right? Molar heat capacity as its molar heat capacity. And by the way, guys, this will be proving, this particular relationship will be proving in kinetic theory of gases. N will be equal to 1. Since we are talking about 1 mole, N is 1. So therefore, PV is equal to RT. Then we also will use delta U is equal to Q minus W. That's one more formula that we'll use. And then we will make use of CV is equal to dQ by dt at constant volume, while your Cp is change in internal energy per degree change in temperature at constant pressure. I think I should make it a bit more clear. See guys, molar heat capacity is to do with how much heat do we need per increase in 1 degree Celsius. And so the formula. Is it not? If you think about the definition, it makes sense. How much energy do we need so that we increase the temperature by 1 degree Celsius? Of course, given the material is 1 molar, right? So that being the formula, this particular expression reflects that. So with all of this in mind, we can start off with the derivation. So we can start off with let me start off over here. So we'll start off with at constant volume. So it makes it very simple. At constant volume, what happens? The work will be 0. Therefore, your change in internal energy will be equal to Q, right? So the small change in internal energy will be equal to the small heat that flows in. And as per this formula, dQ is Cv into dt. This will be Cv into dt. So your du is equal to Cv into dt. Very simple. Now, at constant pressure, of course, work is not 0. Delta U is dependent on Q and the work, right? Delta U is dependent on Q and the work. So here, what do we have? So for a small change in internal energy, we're looking at small change in Q and small change in the work. Small work being done on the system or by the system. Okay, so let's take each term and look at what each is doing. So starting with the work. So work is quite simple. Work done in constant pressure is nothing but P into dV. So this formula we have seen quite some time. Work is equal to force into displacement. From that, we can derive this. Then dQ, when it comes to constant pressure, from here we have Cp into dt. So for constant pressure, we have Cp into dt. And du is Cv into dt. This is from 1. So from 1. Okay, so all this is good. Now, you have Cv into dt is equal to Cp into dt minus P times of delta V dV. So we almost have the answer. If you go to the final answer, we have Cp minus Cv is equal to R. So if I rearrange, I'll get Cp minus Cv. But we have P dV. We need to do something with this. So where do we go? What do we use? Yes, we'll make use of A. I'll call this as A. So from A, what do we have? We have PV is equal to RT. N is 1, remember? Now, we need dV. So for that, we will differentiate with respect to temperature. So this is a product rule. So dP then by dt into V plus P times of dV dt is equal to R is a constant, and this is 1. But since we are talking about constant pressure, this will be 0, as pressure is constant. Differentiating a constant term is 0, right? So as pressure is constant, this will be 0, and we have P dV is equal to R dt. I'm just rearranging the terms. So when we substitute and say 2, we'll call this as 2. What do we end up with? We end up with Cv dt times of, not times, sorry, is equal to Cp dt minus this is R dt. And you can see dt is common, and bit of rearrangement, R is equal to Cp minus Cv. And that's your derivation. That's it. Quite simple. Yes, there are few formulas that we have not yet proved. Like this is something that we have not yet proved. This is from the definition. Okay. And this too is also from the definition. And the rest of it is quite simple actually. Quite a simple math. Okay, yes. So if you want a better write-up, I'll show that also. But yeah, so this is your Mayer's relation. So we have this. Okay, I'll show you this first though. Or let me show that. You guys can decide what you want to write. Okay, so this is the proper lengthy and everything version, and this is a shorter version to quickly understand what we're dealing with, a proper overview.